All right, I wanted to get started here and show you a few things in Excel. Every module that we're doing in this class, I'm adding some new content to try to encourage all of you to use Excel a little bit more because it's something that you'll be using for a long time, most likely. So here in Module 3, let me show you a little bit about what we are looking at. We're basically focusing in Module 3 about solving systems of linear equations, which we did a little bit before with the matrix algebra, but now what we're doing is we're looking at them using some techniques called like Gauss-Seidel and also Gauss elimination. Now, you can use Excel for those, but it's not that easy, and there's no real tool in Excel that's going to do that. Now, of course, there's lots of tools in Excel to solve systems of linear or nonlinear equations, and we'll talk a little bit about that in this video. But specifically Gauss-Seidel and also specifically Gauss elimination, that is something that you would not do in Excel, but it still has value, okay? It still has value. So even though you can't do it in Excel, there's still value because if you have a system of equations and let's say you put it in a matrix and the matrix, you try to do the inverse and it does not exist, or you try to throw it into Excel solver and it says no solution. Actually, you may have a situation when you try to solve the problem where there's no solutions, but you may also have a situation where there's infinitely many solutions, okay? And you will get an error either way, okay? So you might get an error with infinitely many, just like you get an error with no solutions, and that's a pretty big difference, as you might imagine. So Gauss elimination helps us to see whether you have no solutions or infinitely many solutions in that case where there's not one unique solution. But that's not something we can do in Excel, so that's something you should do on your own by hand and look at the videos I've posted. Now, there's a couple things I'm going to show you today in Excel, which I think is going to be useful. First off, when we talk about optimization, we're going to talk about this method called Newton's method, okay? I'm going to show you that. And then the other thing I'm going to do is I'm going to start talking a little bit about the nonlinear optimization and solving nonlinear optimization problems. And so that's another thing that I want to work with you on. So let's go ahead and open up Excel. And here is Excel, and what I want to do is I want to first look at using Newton's method to solve an optimization problem. So I have an optimization problem right here, and you can kind of see it over here. It basically talks about the drag on an airfoil is a function of friction and lift. And what we have here is it has also a function of a couple other variables, but we'll fill those in, okay? In fact, we're going to fill those in, and we're going to write this as this. We're going to write it as drag d equals, the function would be 0.005 times v squared, okay, plus 1.9 times, in this case, it's 15,000 divided by v, and that whole thing is also squared, okay? And so that's the function that we're basically working with right there, okay? You can kind of see, if you look over the right, that basically all I did was I substituted a value of 0.5 for the sigma, and I substituted 15,000 for the w, if you look at the equation on the right there. That's just some just generic numbers that we're plugging in here. But the idea is to figure out the minimum value of drag of this function, and we're going to use the Newton's method. Now, a lot of students get confused by this because the Newton's method sounds just like Newton-Raphson, and in fact, it looks just like the Newton-Raphson method, okay? There's a big difference though, so don't trip this up when it comes to tests and quizzes. When it comes to tests and quizzes and the Newton's method, okay, you use the first derivative divided by the second derivative, okay? When it comes to solving for roots problems and you use Newton-Raphson, that's going to be the function divided by the first derivative. So you might remember the formula. It looks something like this: xi plus 1 equals xi, and then it's equal to minus the function evaluated at xi divided by the function's derivative divided by xi. That's what we learned when we did Newton-Raphson. Okay, that's for solving roots problems, okay, which is basically f of x equals 0, right? But what we want to do is we want to solve optimization problems. This is an optimization problem. We're not saying when does this function equal 0. We're saying what is the minimum value of this function, okay? Completely different problem. And so it needs a different approach. And the approach that we're going to try is called Newton's method, okay? Newton's method looks like this. It still has xi plus 1 equals xi minus, but in this case, it's the function, the first derivative of xi divided by the second derivative of xi, okay? That's a big difference, like that, okay? That's a big difference. It's not the function divided by the first, it's the first derivative divided by the second, okay? Now, in something like this, you better know how to do analytical derivatives, because not only do you need to do one, you need to do two. So we need to get, of that function you see on the right, we need to get the first and second derivative of that function. But you know, it's really not that complicated in that function, because it's just basically a polynomial. Just you've got divided by v squared, so you have to, you know, work through how to do the derivative on that. But I would suspect that most of you could get that derivative analytically. I hope so. And of course, some of you have calculators that can do that as well. Okay, so it turns out, by the way, if you substitute the numbers that we have here, okay, let me go back here. Oops, sorry. Let me go back here. If you take a look at that, let's do this. Okay, if you take a look at that, okay, we can solve for the first and second derivatives, okay? It turns out that the first derivative, and I'm just doing that, you don't have to do this. You don't have to do this, but I'm just kind of, I mean, you have to do the mathematics, but I'm taking more time just to do it. The first derivative, if you work it out, I'll tell you, it's x divided by 100 minus a pretty big number, 855, 6 divided by x cubed. Okay, that's the first derivative. And it turns out the second derivative is 265, no, 2565, 1, 2, 3, 4, 5, divided by x to the fourth plus 0.01. Okay, so that's what you get for the first and second derivative if you do those analytically. Now, here's what I'm going to do. Really easy. We're going to show you how to use Newton-Raphson in Excel. Super easy. All right. So what we're going to do is we're going to establish a cell that has X. So I'm going to say in this case it's cell B8. Cell B8, you know, I'll highlight it if you want. That cell contains X. Now, you know, whatever X I have there, that's where it's going to be. So here's how we're going to do it. We're going to literally type that formula that I just wrote a few cells above for the Newton method, okay? So the new value of X equals the old value, which is B8, minus, now I have to define the function, the first derivative of that function evaluated at X, which is B8, okay? So what's that going to look like? That's going to look like B8 divided by 100, right? And then minus 855 divided by B8 to the third power, okay? That should work. And then we're going to divide that. Now, the second derivative, which is going to be 2565 divided by that to the fourth, okay, plus 0.01. Okay, so if we've done everything correctly, it'll give us a divide by 0 because we don't have an initial guess here. Now, you have to know something about this function. This basically is the a function of drag on an airfoil, like an airplane wing. And so, and I believe the velocity might be in feet per second, meters per second. Doesn't matter. But let's say it's feet per second, and let's say a good guess for that is 100. Okay, cool. So I did 100, and now I got 133.28. Now, the really great thing about this is because I've set this up in Excel, okay, like so, you can see the formula there, right? If I click and drag this down, it will now pull from the new value of X, cell B9, and then it'll keep working through iteratively. So let's try it. Hope it works. There we go. Now you notice something there at the end? It looks like it's converging on a value. Let's do a few more. Yeah, pretty much it's converging, right? It's converging on a value right there, right? So we could say, okay, that looks like that is the minimum velocity, so the velocity that minimizes the drag is really what that is, okay? This velocity v here, okay, this velocity is causes minimum drag. Oops. Min drag at v equals 540.7 whatever, right? Okay, something like that, okay? That's the minimum drag, okay? In fact, I should probably not call this X, I should call this V, but I was using X because that's the formula is in X, but you get it. In this case, it's V, so whatever, right? Okay, so the minimum drag is at V equals 540 feet per second, meters per second, whatever, okay? Here's the key principle here. The key principle is when I define this function, and I wrote it in terms of the previous value, the previous cell, in this case it was B8, and it was only a function of X, then all I had to do is hit enter and then copy paste it down, and it would update, and it would basically help me converge to the value. So super simple, okay? Really easy to do. The only issue, of course, is you need to have both the analytical first and analytical second derivative. Okay, cool. So we've done that, and that's how we use Newton's method. So if you want to, you can call this Newton's method. You can add this to your spreadsheet. You can add more tabs to your own spreadsheet there, okay? So that's one thing I wanted to show you that's related to Module 3. The other thing I wanted to show you is basically using our solver. So we're going to call this optimization, multivariable optimization. I'm sorry, M-U-L-T-I, optimization, and that's using the solver, okay? We'll say, SOL, okay, like that, using the solver, okay? You can title it whatever you want to, but what we want to do is we want to use this solver in Excel. I'm going to make this a little bigger so we can see everything a little easier, okay? And so we can do a lot of things with the Excel solver, okay? It's very, very powerful. It could solve linear equations, linear systems of equations like that we would normally use matrix algebra for, but we could also use it to solve nonlinear equations equal to 0. And then we can also use it for optimization. We can use it for optimization of one variable, or we can use it for optimization of many variables, okay? So what I want to do is show you a harder problem this time. Instead of showing you an easy problem, okay, let's show you a harder problem, okay? Let's show you something that is a little more of a challenge, okay? So the problem I came up with is a optimization. We want to minimize this function, and this happens to be a function of more than one variable. It actually happens to be a function of several variables, okay? So here's what we got. I got the function, it's a function of x and y, and this particular function, I just came up with it, I thought it would be useful, okay? This particular function is 2 times x cubed times y, okay, plus 39.6 times x squared times y, okay, plus 2 times y cubed times x minus 22.2 times y squared times x, finally, plus 57.25 times x times y. Okay, so that is a big equation. and it's clearly a function of two variables, x and y. And let's say I wanted to find the minimum value, minimize that function. So what is the x star and the y star that minimize that function? Okay, what is the x and y values that cause that function to be minimal? Okay, looking at it, I don't know how you would know that. It would not be very clear to anyone what values of x and y minimize that function. You might guess that it's probably near 0 for x and 0 for y. Yeah, but you wouldn't know exactly where it's at. So the good news is we've got the solver, and the solver can do this problem. And if you can do this problem in the solver, which is an optimization of multivariables, then you can do pretty much anything. You can solve systems of linear equations, which should be very easy, or you can do something like this, which is harder. All right, so here's how we do it. Really easy. We're going to set up a variable for x, and we're going to set up a variable for y. So the actual variables are going to be right here. So let's see here. Insert here. Let me just highlight this here. This is different now. Here, let me just do it this way. Format the cells, and we'll border them. How about that? Okay, how about that? Yeah, there we go. Okay, so these two cells here, oh, and I wanted to shade them. Let me just shade them. It doesn't matter. I'm just doing this so you all know where I'm looking at. Okay, so we got an x and a y. Cell D6 and cell D7 are going to represent x and y. And all I have to do is write that function now, but instead of writing it x and y, I'm going to write it as cells D6 and D7, because D6 will be x and D7 will be y. Okay, pretty easy. All right, so now I'm actually going to type the formula in, so it's going to look just like what I typed up top, but now with x and y being cells. Okay, so it's going to be 2 times, this is going to be x cubed times y, okay, plus 39.6 times x squared times y, okay, plus, whoops, let's see, let me go back here. I don't want to goof this up here. I think I'm adding something in here. Let's make sure I don't do that. Okay, let's see here. That was D7. Yeah, that's good. Okay, plus, don't put spaces in there, Excel. I'll be mad at you. Y cubed times x. Okay, that looks good. And then minus 22.2 times y squared times x. Okay, and then it is plus 57.25 times x times y. Oops, not y. Now here I did that. Don't do that. Okay, there we go, D7. All right, so hopefully that's right, and I've typed in everything correctly in terms of the cell references. One of the easiest mistakes you can make is goofing up a cell reference or goofing up a number in here. So you won't get anything in here until you actually put guesses in here. You know, I could put 0 and 0, and of course it's going to be 0, because if you look at that function up top, if you put in a 0 for x and 0 for y, you're going to get 0. But if you put in 1, 1, you're going to get something. You're going to get 78.7 if you add them up like that. So anyway, it doesn't matter what you put in here. What we want to do is use the solver. Now, you find the solver under the data tab, okay, and you should see it all the way over here to the right. If you don't have it, and that's very likely that some of you may not have it, then you need to go to File, and you need to go to Options, and then you need to go here to add-ins, okay? And you actually need to add it in, and you'll see it right here, Solver Add-in, okay? Now, we already have it there, so remember to go File, Options, Add-in if you have not, you have to do that first. Once you do it once, it should be there. Okay, so we're going to hit Solver. We're going to open it up, and it's going to look like that. Okay, it's actually really simple, and it's actually very powerful. Now, sometimes Excel's smart, and it knows what your objective cell is. Your objective cell is that cell that has that function. Okay, so it is correct. It's D9 in this case. The objective cell is D9 because it has that function. Okay, now it says, what do you want to do? Do you want to maximize it? Do you want to minimize it? Or do you want to set it equal to something? Because you can solve an equality as well. Now, in this case, we want to minimize it. So then what do we want to change? What cells do we want to change? Well, we want to change these two cells, the cells D6 and D7, of course. Okay. And then it's like, okay, do we want to have any constraints? Okay. Do we want to have any constraints? Well, in this case, I won't add them, but we could, if you wanted to add constraints, what you could do is say, for instance, I won't do this, but let's say, I'll delete it. Let's say we want to say that the X value can be no greater than 10. Okay, you can do that. Hit OK. And it basically says that cell D6 must be less than 10. Okay, whatever. Or you can just take them out. Okay, no big deal. All right, so we won't do that. Now, the other thing that's important here, it says make unconstrained variables non-negative. That's important because what that means is basically you're never going to consider negative values here for X and Y. Now, in this case, I want to uncheck that because I want to consider negative values. But there are cases when you do optimization that you would not want to consider negative values. For instance, let's say you're making a decision of purchasing at a company and you're saying, well, how much optimize how much steel and how much whatever other materials you've got. Maybe it's aluminum and maybe it's other raw materials and magnesium or whatever. Let's say you wanted to optimize how much you bought of each one. You would never consider buying negative of something, okay? Yeah, another classic problem is optimizing how much sugar and fat and carbohydrates and protein that you eat. Well, you can't eat negative protein, right? So what that means basically is you would check that box, so you never consider negative values, okay? In this case, we'll consider negative values, I suppose. We could look at it. We'll see what happens. How about that? Okay, so we want to minimize this, and we're going to uncheck it because we're going to consider negative values for X and Y that minimize that function. So that's pretty much it. We're going to hit the solver and we're going to say, okay, look at that. Okay, so now what I have here is, hit OK. It gave me a value for X and a value for Y that minimize that function. Okay, and so then what I should do is, let's double check here of this function. Let's double check that I've typed it in correctly here. So, because I've got it here in front of me. So let me double check that. So 2 times x cubed y, okay, that looks good. 39.6 times x squared times y plus 2 times y cubed times x, that looks good, minus 22.2 y squared times x plus 57.25xy. Okay, good. So we've got that function. And now we've come up with a value of x and y there that minimize that function, and we considered all values. Now what you could do as well is you go back here and say, okay, only look at positives. But if you only look at positives, then it's just 0, 0. That's a trivial case. But if you go back here and you say, I'll look at anything, okay, any values in x and y, then, oops, hold on. You go back to solver here, and yeah, you got that, and we're trying to minimize changing those values here. Then, since I don't have anything on there, okay, for some reason it didn't go back to that solution here. Let me try this. Okay, sometimes this thing does some funky stuff. Let's try this. So what's really going on here is that it really depends on, if you take a look at the solver here, it really depends on what your initial guesses are, okay? So when we did this with 0, 0, it says, hey, I got this initial guess. But if you go here and go, let's do -1 and -1, then you put that in there and you go to solver, and it says, hey, look, I've got this other one right here, -8.8. But if you look at another guess like this, -4, -2, you probably can go back and find that solution, which I believe is the actual minimal solution that you're going to find. So what you do have to realize in this method is that you might be converging to a local minimization, but not the overall global min. Okay, so be careful with that as you go through it. So anyways, this is a very useful tool, the solver. Be careful that it may not give you always the global max or min. It's just going to stop wherever it thinks it can find it. And sometimes these very complicated type of problems, it's not very clear where the max or min is. And that's why sometimes you may want to put constraints on it. For instance, you may only want to search between -10 and 10 or something like that. Okay, you can do that very easily. But again, very powerful tool, and you should definitely get to learn your solver.